Hello and welcome, class. For today we are going to be finishing up chapter 5. So far we have talked about all of the constructions and naming conventions for ionic compounds, molecular compounds, polyatomic compounds, as well as acidic compounds. So all of the different naming conventions and all of the different formulas that we've talked about at this point are now behind us. We're going to be using them with great regularity as we continue to talk about molecules and how they come together and what their properties are. But before getting ahead of ourselves, it's important to ask the question, how do we know? How have we determined these chemical formulas, and how do we have confidence in what our findings are? For that, we are going to now turn to the quantitative. We are going to talk about determining percent compositions by mass. So of all of the devices and all of the instruments that we have, what we are going to introduce today is known as the mass spectrometer and how it helps us to figure out what the chemical formula for the ionic compounds, molecular compounds, etc. are that we work with. So what a mass spectrometer does is it breaks your compound into ionized pieces. So whether you're working with an ionic compound or a molecular compound, we are going to put our sample in here, whatever it might be, and as the sample shuffles along in the tube, it's going to be hit by an electron beam, it's going to be hit by this heater that's going to vaporize the sample, and even if you're working with a molecular compound, it will break it into ionic pieces. The purpose of this is as we shoot or accelerate the ions through the device via these charged plates, they're going to come into contact with a magnetic field from these magnets being presented around it. What the magnetic field does for us is it separates our ions by a mass to charge ratio. So the lightest ions with the greatest charge are going to be deflected the most. So we'd have, let's say, light ions here on this side, and the ions that get deflected the least are going to be the ones that are the heaviest. So the largest ions deflected the least. All right, so for every one of these beams that ends up hitting our detector, we end up with a report on the other end. Like the detector picks up all of these pieces. It's like, it seems like whatever the sample was has broken into 1, 2, 3, 4, 5 pieces with certain charges, and all depending on how much they deflected, we can get a mass to charge ratio. The instrument then kind of crunches these numbers and gives us a mass percent for the composition. So let's say hypothetically we put in something that's like a certain amount of A and a certain amount of B, and we don't know what these subscripts are. We don't, we might have an idea for what A and B are, whatever they might be. So we put in the sample, it runs through the mass spectrometer, and in the simplest, again, most kind of generic sense, our instrument is going to give us then a report for your sample is 65% A, and what would that be, 35% B. Now this itself doesn't give us explicitly a chemical formula, but we can use these percentages to figure out a chemical formula. So that's where we're going with all of this today. We're going to first observe what it means to be a mass percent composition, and then once we have a better idea for this, we are going to use it to determine chemical formula. All right, so percent composition, also known as mass percent or elemental composition. Each of these terms is interchangeable with each other, at least in general chemistry. The percent composition is the percent of an element's contribution to the total mass of a compound. Now here below we can see an explicit equation representing this definition, where the mass percent is equal to the total mass of an element inside of a compound. And this is going to be divided by the total mass of the compound. So just like any percentage, we're looking at a part divided by the whole, or a fraction divided by the whole. And of course, because it's a percentage, we're going to multiply this by 100. Now, in order to determine the total mass of an element inside of a compound or the total mass of the compound, we are going to be using the atomic/molecular masses present in the unit of AMU from the periodic table. So we're going to return to using the periodic table in all of its useful glory in order to predict what mass percentages are for certain compounds. So the first example of the day that we are going to work through is determining the percent composition for each of the elements, carbon, hydrogen, and oxygen, inside of table sugar. So we have sugar, which the formula is C6H12O6, also pictured down below. So what we're going to be doing is figuring out what the percentage of carbon's contribution is to the mass, hydrogen's contribution to the mass, and oxygen's percent contribution to the mass. Now, if you are working along at home, again, please take a pause, try and use our previous equation to determine the mass percent for yourself. But if this is after the pause, then welcome back. Let's use that equation to figure out what the mass percent composition for each of these elements in the molecule is. All right, so our equation, just to go backwards, has two different parts that we're trying to figure out, right? Either the numerator's component or the denominator's component. Times 100 is always going to be times 100. So we are looking for the total mass of an element in the compound, and we're looking for the total mass of the compound. So let's actually start with the denominator. It's going to be the easiest thing to look for because we've actually already found this type of thing before. The total mass of the compound is going to be equal to the formula weight of the compound in the unit of AMU. So we're going to take all 6 of our carbons, all 12 of our hydrogens, and all 6 of our oxygens and add all of the masses together. 6 times the mass of our carbon on the periodic table is 12.01 AMU. We're going to take that and add it to 12 times the mass of hydrogen on the periodic table, which is 1.008 AMU. And we're going to add that to 6 times the mass of oxygen on the periodic table, which is 16.00 AMU. We crunch these numbers in our calculator, and what we find is that the total mass of our molecule is going to be around 180.2 atomic mass units. So this is going to be what we place in the denominator of each of our mass percent calculations. So I'm just going to block that off down here. And we have all of the rest of the space up here to crunch the numbers for the carbon, the hydrogen, and the oxygen. All right, so we still have to find, though, the numerator for each of these calculations. Well, what the numerator is meant to represent is the total mass of an individual element's contribution to the total molecule. So in carbon's case, there are 6 carbons inside of this molecule, meaning that its contribution to the mass is going to be 6 times 12.01 atomic mass units. So literally, basically what we're doing is we're going to take carbon's contribution to the total mass down here and just put that into the numerator and divide that by the whole, which is 180.2 AMU. And then of course times by 100. But if we continue to set up the rest of these elements before crunching these numbers, we can really see this pattern. Hydrogen's contribution, we can see also down below, 12 times 1.008 AMU, all divided by that 180.2 AMU. And again, percent, so times by 100. And oxygen's, we can see last. It's that 6 times 16.00, all divided by 180.2 AMU. And again, all times 100. So we can see that each of these individual pieces from our calculation of the total mass just get broken up and placed in the numerators corresponding to each individual element that we're focusing on. So carbon's comes first, hydrogen second, oxygen third, and now we have 3 individual calculations for finding the mass percent contribution of each of these elements inside of table sugar. All right, so carbon, we crunch these numbers, we find that its percent contribution to the mass is 40.0%. Hydrogen, coming next, is 6.71%, and oxygen, coming last, is 53.3%. So carbon may only be 6 of the atoms inside of this molecule, but it contributes 40% of the weight. Hydrogen, in great contrast, may be half of all of the elements present inside of this molecule, but in terms of mass, because hydrogen is so incredibly light, it's only 6.71% of all of the mass that's found inside of table sugar. Oxygen comprises the majority of the mass because it is the heaviest of all of the elements present inside of the chemical. And if we were to take table sugar, just to go back, here, if we were to take table sugar and insert it here, C6H12O6, run it through our mass spectrometer, our detector on the other end would say, it'd have to print off a graph, we'd read the graph, and we'd be like, what it's telling us is that we have 40% carbon, 6.7% hydrogen, and 53% oxygen, if I'm just cutting off the decimals here. So that's what our mass spectrometer does. We put in a sample, and it tells us what that mass percentage breakdown is on the other side. And if we didn't know what each of these subscripts were, it would still tell us what the percent breakdown is, right? We don't have to tell it the chemical formula. It's just absorbing, it's like eating, it's breaking down the compound that we put into it, and it's spitting out on the other end these mass percentages. All right, so where we are going from here is how do we take these mass percentages and put them back together to find a chemical formula, right? That's what all of this is about. How do we find chemical formulas from experimental results? Well, now that we've broken down what it means to be a percent composition, we can get a good vibe, a good feel for what it means to go in the reverse direction. How do we start with a percentage and go backwards to finding those numeric subscripts? How we do that is a little bit complicated. We cannot simply use the mass percent equation to quote unquote go backwards because there are 2 unknowns and 1 equation, right? We don't actually know what the total mass of the individual molecule is if we don't know the subscripts, and we can't find the elemental contribution to the mass because we don't know the subscripts. That's what we're trying to find. So what we need to do instead is get a little clever. We're going to use mass percent to first find the number of moles present for each element in the compound. So if we start with mass percent, we can find mass, right? Since we just have to convert out of the percent and into a mass, assuming that we know what the total mass of sample is, not the mass of the molecule, right? That's unknown. But if we know, I took a scoop of like 5 grams of question mark and put that into the device, that's going to be what's important to us. If we know the total mass of the sample itself, we can use that to get out of mass percent and into mass. And from mass, we can then individually get into numbers of moles for each of the elements. Now, the important thing about getting into the mole is, as a reminder, the mole is a counting unit. It deals with amounts of things, not masses, not weights, but numbers of things. So if we start with mass and use it to convert, or if we start with mass percent, and use it to convert into mass and then moles, what we are literally doing is figuring out, if we're starting with like 10% of mass comes from hydrogen, bada bing, bada boom calculation, that must mean that I have 4 moles of hydrogen. And now that you know how many moles of hydrogen you're working with, you also technically know how many atoms of hydrogen you're working with. And if you know the numbers of the elements you're working with, that's the same thing as knowing your formula subscripts. And of course, we're going to work through an example of this, so if the flowchart just seems kind of like too abstract at this point, we will be grounding it in a real example, so it will be fine. But the end of the road, the end of the flowchart, is if we have our formula subscripts, we can reduce them down to find the lowest whole numbered ratio, aka the empirical formula. So if we are working with an ionic compound, something, right, that has positive and negative charges, this is the end of the road. Once we know the empirical formula, we know what the ionic formula is because they're the same thing. If, however, we are working with molecules, there's going to be an extra special step after this that we're going to talk about in a little bit to figure out the molecular formula as well. But I think just observing the first part of this flowchart is going to be enough to start with. So let's break down going from mass percent to numbers of moles, and from numbers of moles to the empirical formula. All right, so this is an example we're going to do together. Let's say we have an unknown sample of something. We put it into a mass spectrometer. It crunches the compound down, and on the other side, boop, 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 it tells us that we have 39.97% carbon, 13.41% hydrogen, and 46.62% nitrogen in this sample. Right, so it's broken the sample down into ions, detected what percentage of each of these compounds we have on the other side. So now from here, we can take these mass percentages, using the flowchart that I've just outlined, we can backtrack the long way and figure out what the subscripts are for each of these elements are in the compound. All right, so no more chatter. Let's actually do it, right? The best way to learn this type of problem is to do. So what we're going to do first, 1, assume a 100-gram sample of unknown. And it may seem a little bit like cheating just to assume what the initial mass was of our sample, because like what if it wasn't 100 grams? It turns out since we're working with percentages at the start, it doesn't really matter. The calculation from here on out, because we're working with a percentage, which is technically a ratio unit, everything's going to be self-consistent with whatever we start with. So if we start with 100 grams, it turns out that it's just going to greatly simplify our calculations as opposed to starting with what the mass might have actually been. So if we, number 1, assume a 100-gram sample of our unknown, all of the rest of our calculations will be self-consistent due to us starting with percentages. So if we assume a 100-gram sample times 100 grams, what this is going to tell us is out of this 100 grams, what percentage of this 100 grams is carbon. It will also tell us what percentage of this 100 grams is hydrogen, and it will tell us what percentage of this 100 grams is nitrogen. Well, if you want to figure out what 39.97% is of 100, turns out that's just equal to 39.97 grams. And 13.41% of 100 is 13.41 grams. This is carbon, hydrogen, and similarly, 46.62% nitrogen out of 100 grams is 46.62 grams of nitrogen. And here we can see exactly why we assume 100 grams of our sample initially. It's because our first step in the calculation is literally dropping the percentage and swapping it out for grams. If we assume a 100-gram sample to start with, we can always make this shortcut. Drop the percentage, swap it out for the unit of the gram, and this will be consistently true so long as we are assuming, again, a 100-gram initial sample. All right, so now, to go back to the flowchart, we have gotten out of the unit of the percent, we are here, we are in the unit of the gram. Our next step is to get into moles. It's been a while since we've done this type of calculation, but we can use the molar masses found on the periodic table in order to get out of the unit of the gram and into the mole, because the unit of the molar mass is grams per mole. It's literally the perfect conversion factor to get us into and out of grams and moles. All right, so the molar mass of carbon on the periodic table, all we have to do is look at what that like mass number is. That's going to tell us how many grams are in 1 single mole of carbon. So there are 12.01 grams of carbon per every 1 single mole. And there are 1.008 grams of hydrogen per every 1 single mole. And there are 14.01 grams of nitrogen per every 1 single mole. Equal, equal, equal. And this is going to give us now, in terms of a counting unit, how many carbons, hydrogens, and nitrogens we're actually working with. Like how many were put into the machine. In crunching these numbers, what we find is that we are working with 3.328 moles of carbon, 13.30 moles of hydrogen, and 3.328 moles of nitrogen. So now we are working with counting units. We are working with numbers of things, not just what they weigh, but how many of them there are. Like using Avogadro's number, we could even push this one step further to figure out exactly how many atoms we're working with, but that's kind of unnecessary based off of the fact that we're just looking for ratios here, right? We're not actually trying to find numbers of atoms. We're trying to find how many carbon atoms there are relative to how many hydrogen atoms there are relative to how many nitrogen atoms there are. And so for this reason, now that we are in the unit of the mole, which is a counting unit, we can just take that and drop it into the formula subscript of some type of chemical formula. We're going to take each of these numbers of moles and drop them into the subscript for our chemical formula. And this is going to look a little strange since we don't normally represent chemical formulas with decimals, but we have 3.328 moles of carbon. We have 13.30 moles of hydrogen, and we have 3.328 moles of nitrogen, which means we have roughly 3 to 13 to 3 parts of carbon to hydrogen to nitrogen, respectively. Right, and this only works if we are in the unit of the mole, because the mole is a counting unit. We want each of these ratios here to be in a type of a counting unit. Super, super important. This won't work unless we're in the mole. Since we are in the mole, though, we are totally free to take these values, drop them into the subscripts, as we have done here. So we have roughly, again, 3 parts carbon, 13 parts hydrogen, and 3 parts nitrogen. Well, in order to clean this up and make it actually look like a chemical formula that we're more familiar with, just to go back to our flow chart, we are currently here, we are going to reduce our subscripts down to the lowest whole numbered ratio. We are going to write our chemical formula as an empirical formula first. So in order to write this subscript, or these subscripts, as the lowest whole numbered subscripts, we're going to divide each of them by the lowest present. So we have to ask ourselves which of these values is smaller. Is 3.328 smaller, or is 13.30 smaller? Duh. 3.328 is the smallest of all of the values present. And so we're going to divide each of these subscripts by this 3.328. This is going to simplify all of these subscripts present into their lowest whole numbered ratios, where 3.328 divided by 3.328 gives us a subscript of 1. 13.30 divided by 3.328 gives us a subscript of 4. And again, 3.328 divided by itself just gives us a subscript of 1. And so here now we can see that we started with mass percents. Again, assumed a 100 gram sample first. 2, converted into moles, which is what we did here. 3, we took those moles and inserted them into the subscript of some makeshift chemical formula. And then last but not least, we reduced all of those chemical formulas down. So if we were starting with a sample that was 39.97% carbon by mass, 13.41% hydrogen by mass, and 46.62% nitrogen by mass, what we're really working with was a chemical formula that was 1 part carbon, 4 parts hydrogen, and 1 part nitrogen. All right, so now that we've worked through an example together, I would like you guys to pause the video and try an example by yourself. So what is the empirical formula of a compound that contains 60% carbon, 4.48% hydrogen, and 35.53% oxygen by mass? All right, well, if you were working through this problem and you got to the end and found something a little strange, then let's address that. And if you didn't find something strange and you're like, oh no, I didn't find something strange, that's okay too. Maybe you did find what I'm referring to, you just didn't think it was strange. So let's work through this problem together and then address any strangenesses that might have occurred along the way. All right, so we're starting with 60.00% carbon, 4.48% hydrogen, and 35.53% oxygen, all by mass. So just like before, our first step is going to be that we are going to assume 100 grams of our starting material. And this is going to allow us to drop the unit of the percent and insert the unit of the gram. So we're actually working with 60.00 grams of carbon, 4.48 grams of hydrogen, and 35.53 grams oxygen. All right, so that's rule number 1, or step number 1, is what I should say. Right, get out of the percent and into the gram. Now the next step in our flowchart is to get out of the gram and into the mole. So we're going to use the molar masses present on the periodic table to get out of the unit of the gram and into the unit of the mole. Carbon's mass in the periodic table is 12.01 grams for every mole. Hydrogen's is 1.008 grams per every 1 mole. And oxygen's is 16.00 grams per every 1 single mole. All right, whipping out the calculators, crunch, crunch. What we find on the other side is that we are working with 4.996 moles of carbon. We are working with 4.44 moles of hydrogen, and we are working with 2.221 moles of oxygen. Now, just like before, our next step, now that we have the moles present, is to take each of these molar values and drop them into the subscript of some type of chemical formula. So we have 4.996 carbons, we have 4.44 hydrogens, and we have 2.221 oxygens. So far, so good. The strangeness is going to become more apparent as we reduce our subscripts, or at least attempt to. We're going to take the least or the lesser value of everything present, this 2.221, and divide all of the subscripts by this across the board. Right, this is how we properly reduce our subscripts to the smallest whole numbered ratio, except carbon doesn't really give us a nice whole numbered ratio. If we crunch this number, 4.996, and divide it by 2.221, what we end up with is 2.25. And this may seem like a small enough decimal that you might have just assumed that we can round down, but if we're thinking conceptually about this, 0.25 is equal to 1/4. We have 1/4 of an extra atom here. When we're working with something on the very small scale, 1/4 of an atom is actually pretty sizable. So we can't just round this 1/4 down. We're gonna have to keep it here for a second. The hydrogens will reduce down nicely though to 2, and the oxygen will obviously reduce nicely down to 1, since you're taking 2.221 and dividing it by itself. So what do we do with this carbon? Well, the subscripts are ratios. Right there, we have 2 1/4 carbons for every 2 hydrogens and 1 oxygen, and we found this by scaling down. Well, if we can scale our subscripts down, can we not also scale them up? The answer there is yes. Like everything here, the subscripts are all, again, ratios. So long as we manipulate one ratio, or so long as we manipulate all ratios in the same way that we manipulate one, it's totally fair game. So if we scaled each of these decimal values up on top down by 2.221, we can now scale each of the resulting decimals back up in order to remove this fraction. So since 0.25 is equal to a quarter, we're going to multiply each of these subscripts by 4. This is going to remove the fraction that is currently present on that carbon, giving us 9 carbons for every 8 hydrogens for every 4 oxygens. And this is the empirical formula for the compound that we are working with. All right, so you might ask yourself a question then, which is, well, how would I know that this 0.25 is too large to round down? Like, when is it safe to round versus when do I have to take these decimals into account? And the answer there is, well, rather, how I should say this is to answer your question, I'm just going to pose another question. Is your decimal clearly a fraction? Are you working with 1/4? Or are you working with 1/3? Or are you working with 1/2? If your resulting subscript, just like this carbon was a 2.25, if your resulting subscript is a really nice and obvious fractional value, chances are you can't round, you're going to have to scale up in some way. So if our subscript would have been a 0.33, we're gonna have to scale everything up by 3. If our subscript is a 1/2 in any way, we're gonna have to scale up by 2, right? We're gonna have to scale back up in order to remove the fraction. In doing so, our resulting formula does look pretty hefty, right? We have 9 carbons, 8 hydrogens, 4 oxygens, but this is the lowest, or the smallest, how do I say this? The lowest whole number reduction. There we go. That's how I want to phrase it. This is the lowest whole number reduction of all of the subscripts without turning anything into a fraction like how we had before. So how you know when to round? Your value, after reducing your subscripts, should be really, really close to an integer value, something like on the level of 0.9. If your value, though, is further away than 0.9 or like 0.00 something, if it's clearly closer to a fractional value, keep that fraction, and then as we did in this example here, scale it back up to remove the decimal. All right, so far we have found mass percents, so we can kind of demonstrate where these percentages come from. And then now we have learned how to use these mass percents to find empirical formulas. But there is one step left, which is if you're working with a molecular compound, as we've learned it's important, you can't represent a molecular compound with an empirical formula. You need to have a molecular formula. So how do we take this next step? Subscripts in molecular formulas are always whole numbered multiples of those in the corresponding empirical formula. In other words, if we can scale our formulas down to the empirical formula, we can always scale it back up with the same factor that we divided it down by. So like, let's say if we're taking C6H12O6 and we want to scale this down to the empirical formula, we're gonna have to divide everything by 6, right, to create CH2O. Well, if you want to go in the reverse direction, if you want to go from empirical back up to the molecular formula, you're gonna have to multiply by 6, right? So if you reduce down by a particular fraction, you're going to have to scale back up by that same factor. This factor is known as N. How to find N is by taking the compound's molar mass, and you are going to divide it by the empirical formula's molar mass. For instance, the molar mass, the total mass of C6H12O6 is 180.2 atomic mass units. And the the formula weight, the mass of this CH2O is 30.03 atomic mass units. if you take the first and divide it by the other, if you take 180.2 atomic mass units and divide it by 30.03 atomic mass units, so the compound's molar mass divided by the empirical formula's molar mass, what you get is 6. And this represents the factor that we can use to scale up our empirical formula, as we did here, to get back to the molecular formula, your actual compound's formula. All right, so these compound molar masses, where do these come from? We can find them experimentally using either advanced gas law studies, which we're going to be learning about in Chapter 11 in the spring, or using colligative properties, so solution studies, in Chapter 13, we're also going to be learning about in the spring. So for now, what I'm going to be doing is giving you guys like the compound molar masses that you might need, either present in atomic molar or atomic mass units or in grams per mole. But so long as we are working with the same unit here, where again, these values numerically can be found by looking at the periodic table, I will be giving you compound molar masses, and in the spring, we'll be learning how to actually experimentally find them for ourselves. So that's gonna be pretty fun, but we're just gonna put a pin in that for now. All right, so if you have an empirical formula from your mass spectrometer calculation, and I give you some type of compound molar mass, you should be able to find what the actual molecular formula for your unknown is. For instance, if the molar mass of an unknown compound is found to be 60.10 grams per mole, either by using, again, gas law kind of observations or aqueous observations, which we'll be learning about later, and you've also found its empirical formula is equal to CH4N already using mass spectroscopy, what is the molecular formula? All right, so assuming that you've taken a pause and now have unpaused, let's kind of compare our results. So in order to scale up our empirical formula, we're going to need to know what to scale it up by. In order to figure out what this factor is, in order to figure out what the scaling factor N is, we're going to have to take the unknown compound's molar mass, this 60.10 grams per mole, and we're going to have to divide it by the empirical formula's molar mass, which is going to be inserted right here. Well, the empirical formula's molar mass we're going to have to find by observing the periodic table and taking into account each of the carbons, the hydrogens, and the nitrogens here. So in the empirical formula, there is one single carbon with a mass of 12.01 grams per mole. There are 4 hydrogens, each with a mass of 1.008 grams per mole. And our nitrogen, just one of them, with its mass of 14.01 grams per mole. So we can see that the denominator is comprised of a bunch of different pieces. You could just calculate this empirical molar mass outside of the denominator and then insert your answer. Either way should work, so long as the total compound, the unknown's molar mass, is up on top and your empirical formula is down below, you should come up with some type of whole numbered factor. Well, in this case, we're going to be taking 60.10 grams per mole and dividing it by the sum of everything in the denominator, which is 30.05 grams per mole, which is pretty obviously 2. Well, if your N is equal to 2, that means that each of these subscripts in your empirical formula must be scaled up by 2 in order to get to the proper molar mass for your actual unknown compound. So if you take each of your subscripts and multiply it by 2, we end up with C2, H8, N2, and this is the molecular formula for our unknown compound. All right, so we've talked about mass percents. We've talked about using those mass percents to find an empirical formula. And here, the last demonstration of the day, we showed how to find this factor N and use it to scale your empirical formula up to your actual molecular formula. And that's going to be where we call it a chapter. So we have, over the course of this entire chapter, introduced all of the different types of compounds, naming conventions that we're going to be using for molecules moving forward in the semester. And we've also talked about how to quantify and find experimentally these chemical formula. So present compositions of compounds, it's like the first thing that we talked about today. Using molar masses to find the like actual molecular formula. Oh, sorry, my brain just like a little bit. But we can use, or like get some good practice using these problems to kind of reinforce the lessons learned today. All right, if you have any homework, do your homework. And until next chapter, class is dismissed.